The universe was quiet for a long time, 100 million years of just dark. That was the cosmic dark age, and then something changed. That endless night finally broke. The first stars ignited. That was over 13 billion years ago. That single dawn, it built the galaxies. It forged the atoms that make you. That make me. So the question is, what cosmic recipe does that? Turns a dark void into light. And how could the death of those first stars hold a secret? The secret to us being here, to our existence, it means our story, it starts there, in that first flash of light, in the dark. That dark sea wasn't perfectly smooth. It couldn't have been. If it was, we wouldn't be here. It was a soup, a primordial ocean of just hydrogen and helium. But in that haze, the universe kept a secret from its very beginning. Tiny quantum ripples, imperfections almost too small to describe, like the surface of a still pond, and the faintest dimple on it. A variation in density so slight it's more a suggestion. Those were the blueprints, the cosmic seeds. Without them, gravity had nothing. The gas would have just spread out, thinner, colder, forever, a permanent dark age. But those tiny wrinkles in spacetime were the gift. From the young universe to its own future. They were the places where the story could begin. Gravity is patient. It saw those slightly denser patches in the fog, and it began to pull. For tens of millions of years it pulled, gathering that hydrogen and helium around the quantum seeds. This was the invisible scaffolding, the preparation for a birth the universe had never seen. The stage was set, not for a gentle flicker, but for a storm. A storm of creation. Gravity worked in silence, there was nothing else. In that cold dark, it was the only thing shaping anything. Those tiny wrinkles, those quantum seeds, were the only plan it had. And it followed them with a patience we can't really grasp. For 100 million years, maybe 200 million, it just gathered. It pulled the thin, featureless fog of hydrogen and helium inward. The universe was expanding, but inside it, these pockets were doing the opposite. They were collapsing. They were becoming real places. We call them mini-halos. The name sounds gentle, but they were titanic. Vast, swirling spheres of dark matter, invisible, mysterious, and their gravity was a trap. The primordial gas flowed into that trap. You could think of it as the first architecture. The dark matter was the frame, the invisible skeleton. And the ordinary gas, the hydrogen and helium, that was the material that filled it in. This wasn't a gentle drift. As these clouds grew, they started to spin. They flattened into vast, churning disks. Chaos was slowly being given a shape. These weren't stars yet. They were the nurseries, the cradles, the first construction sites with no light of their own, operating in the dark. For eons, the only thing in the cosmos was the silent pull of gravity, drawing the gas tighter. The temperature began to rise at the very centers of these clouds. Pressure built. The simple ingredients were being compressed, prepared, wound up like a spring. The dark ages weren't just ending. They were gathering a final breath, holding it before the scream of light that would tear it all apart. What could be born from that kind of buildup? A star unlike any that has shone since. A hot, puffy gas cloud can't just become a star. It has to cool first, it has to collapse, and for that to happen, the universe needed a new chemistry. The first atoms were loners, hydrogen atoms drifting alone, and they were bad at getting rid of heat. The heat that gravity was building up inside those collapsing clouds. It's like trying to squeeze a hot air balloon. The gas pushes back, it gets hot, and that heat creates pressure. A force fighting gravity's pull. So for a star to form, that heat had to escape. The cloud had to shrink. It had to get incredibly dense, and for that, the universe had to invent a molecule. It began with a collision, two hydrogen atoms drawn together in the cooling gas. They didn't bond easily. It was a fragile union, but it created something new. Molecular hydrogen, two atoms linked together. This simple molecule was a revolution. It was the universe's first refrigerator. A single atom holds onto heat, but a molecule can shake it off, it can vibrate, it can rotate. and in doing that, it radiates energy away. Infrared light. It cools itself down. That was the chemical key, the quiet key that unlocked everything. As these molecules formed in the minihalos, they began to bleed away the heat. The thermal pressure holding the cloud up. It started to fade, and with that resistance gone, gravity won. It pulled harder, faster. The cloud core shrank. From the size of a solar system down to something you could almost picture. The density soared. The temperature at the center climbed from a few hundred degrees to thousands. Then tens of thousands. The gas wasn't just a cloud anymore. It was a protostar, a seething, spinning ball of potential, held together only by its own weight. Inching closer to ignition, all because of a simple partnership. Two atoms forged in the cold. Without that molecular hydrogen, the first stars might have stayed trapped. Just warm, glowing clouds, never crossing over into true light. So before the fire, there was the chill, a necessary cold that made the eventual heat possible. That fragile molecule was the final piece. The heat started to bleed away, and the collapse became a runaway event. The core of that cloud crossed a line. It became a protostar, and at its very center, the temperature reached 10 million degrees. That number is a threshold. It's the moment when the universe learned how to burn. Nuclear fusion ignited. The first true star was born, and it was not like our sun, not even close. This was something else. Astronomers call them population 3 stars. The first generation, they were made from the purest ingredients, just hydrogen and helium, the two elements the universe began with, no heavier elements. No cosmic pollution to change the recipe. This purity and the sheer amount of fuel gravity had gathered, it created monsters. Imagine a star not hundreds of thousands of miles across, but millions. A star not 1 times the mass of our sun, but hundreds of times. Behemoths of pure hydrogen, glowing with a ferocious blue-white light we can hardly picture. Their physics was different. With that much mass, the pressure at their cores was unimaginable. A crushing, relentless force, and that pressure drove the nuclear furnace at a terrifying rate. Fusion didn't just begin, it exploded into a frenzy. These stars didn't simmer for billions of years, they lived fast, brilliant and violently short. They burned through their pristine fuel in just a few million years, a cosmic blink, and in that brief, incandescent life, they changed everything. We have never seen one. Not directly, their light is too ancient, too faint, stretched into the infrared by the expansion of the universe. They are the ultimate ghostly mystery of cosmology. But we know they must have existed. We see their signature everywhere, in the chemistry of the oldest stars we can observe, in the faint glow that permeates all of space. Their existence is a shadow we infer from the impact they left behind. And that impact began the moment their short, furious lives came to an end. That molecular chill, that fragile cold, it set the stage for the final collapse. And at the core of that protostar, the conditions became something new. Something the universe hadn't seen yet. The density was just staggering, like taking a mountain and crushing it down to the size of a pebble. And with that density came heat. A heat that just kept building, from thousands of degrees up to millions. It was a place of unbelievable pressure, where the basic ingredients of everything were squeezed past any limit we'd recognize. You had these hydrogen nuclei, which are just single protons, and they were being forced together. Normally, they repel each other. It's like trying to push 2 strong magnets together, the same ends. They push back. But here, the pressure and the temperature were so extreme that this repulsion, this natural force, was just overcome. The protons slammed into each other. And in that collision, something new was made. They fused, that's nuclear fusion. 2 protons became one heavier nucleus, a step toward helium, and in taking that step, a tiny bit of mass was converted. Turned directly into pure energy. One fusion event, it gives off a minuscule spark. But here, in the heart of this furnace, it was happening countless trillions of times every second. A cascade of sparks became a flood. A torrent of energy was let loose, not as heat or motion, but as the most basic form of light, photons. For the first time in over 100 million years, the dark cosmos had a new light source. Not the fading afterglow from the beginning, but a fresh, fierce, sustained nuclear fire. This was the ignition, the first true dawn, and that outward rush of energy from the core, it created something vital. Pressure. For eons, gravity had been pulling inward with nothing to stop it. Now, for the first time, it met a force pushing back. The radiant pressure from those new fusion reactions pushed against the star's own crushing weight. A delicate balance was struck, a dynamic one, and this balance, this tug of war between gravity pulling in and fusion pushing out, that's what defines a star. It's what makes a star stable. Lets it shine steadily for millions of years instead of just exploding or collapsing right away. In that instant of equilibrium, a true star was born. Its first light, born in the chaos of the core, began a slow fight to get out. It had to push through the dense layers of gas still shrouding the star. It took tens of thousands of years for that initial flash from the center to finally reach the surface and escape into space. But when it did, it pierced the primordial darkness. A single point of blue-white fury in an ocean of black. The cosmic dark ages ended, not with a whimper, but with the roar of a nuclear furnace, and this new light carried a message with it. A signature written in its color and its intensity, and that signature would begin to change the entire universe. That first nuclear fire ignited deep in the core. But the light couldn't get out. The star was wrapped in a dense shroud, the same gas that had collapsed to form it. The universe was still full of neutral hydrogen. And for a photon, that gas was like a thick fog. Think of shining a flashlight in a dense forest. The beam hits a tree almost immediately, scattering. That's what happened to every photon from that first star. The moment it left the surface, it was caught. It traveled a short way, maybe the width of our solar system, before hitting a hydrogen atom. The atom absorbed the energy, got excited for an instant. Then it re-emitted that energy, sending a new photon off in a random direction. This wasn't a journey. It was a chaotic stagger, a random walk. One step forward, several steps sideways, for a single photon of that first light. Escaping the area around its own star could take an almost unimaginable time. Tens of thousands of years, just to break free from the local nursery. This was the last grip of the Dark Ages. Light was born, but it was still trapped. The universe wasn't completely dark anymore, but it wasn't transparent either. It was murky, glowing faintly from within like fog lit by a distant street lamp. You could sense the light was there, but you couldn't see the source clearly. This battle between light and fog defined an era. Every new star that ignited faced the same struggle. Each one was a lonely beacon, its brilliance muffled by the material that had created it. The universe was trying to clear its throat, to push back the haze. And it would succeed, not through a gentle clearing, but through a storm of radiation so intense it would scorch the cosmos clean. That first light was trapped. It was caught in a fog, but the furnace where it came from, that was relentless. These weren't gentle suns, they were titans, burning with a ferocious blue-white intensity. Their light wasn't just visible. It was dominated by something more powerful, ultraviolet radiation, the highest energy light there is, a kind of cosmic bleach. And it poured out from those first stars. It poured out in torrents. This ultraviolet light didn't just bounce off the hydrogen fog, it slammed into it. Each photon carried enough energy to do something brutal. It could rip an electron clean off a hydrogen atom, stripping it bare. That process is called ionization. And for the hydrogen gas that filled all of space, this was an apocalypse. An atom-by-atom dismantling of the fog that had shrouded everything. Where a star shone, it wasn't just making light. It was carving out a cavity, a growing bubble of clear, ionized gas. Inside this bubble, the hydrogen was no longer neutral. It was a plasma, a soup of free electrons and bare atomic nuclei, and crucially, to light, this soup was nearly transparent. photons could finally fly straight. They could travel for thousands of light years, then millions without being absorbed. The universe in these pockets was becoming see-through. This was the epoch of reionization. Not a single event, a slow, creeping dawn. Imagine a vast landscape, covered in a thick, freezing mist, and across that landscape, people begin to light bonfires. Not small campfires, roaring, towering infernos. Around each fire, the heat and light burn away the mist. They create a clearing. At first, these clearings are isolated. Islands of visibility in a white sea. But as more fires are lit, the clearings grow. They begin to touch, to merge. Over hundreds of millions of years, the entire landscape is slowly revealed. As the mist retreats and finally vanishes, that is what happened to our cosmos. Each of the first stars, and the small, early galaxies that followed became one of those bonfires. Their ultraviolet radiation burned bubbles in the primordial fog. And as structure grew in the universe, as stars and galaxies became more common, these bubbles of transparency grew. And they merged. It was a patchwork process, uneven and chaotic. Some regions cleared early, others held onto their neutral hydrogen for longer, but the tide was irreversible. The fog was being systematically scorched away by starlight. This was the true end of the Dark Ages, not the instant the first star flickered on, but the moment, hundreds of millions of years later, when the last pockets of neutral hydrogen were finally ionized, when the fog lifted for the last time. From that point forward, light had freedom. It could traverse the vast gulfs between galaxies without being scattered. The universe became a place where information carried by photons could travel almost forever. This transparency is the sole reason we can look back in time. The deep sky surveys, the ones that show us galaxies from when the universe was young, they depend entirely on that ancient clearing. The reionization epoch was the universe opening its eyes, and in that new clarity, a hidden consequence of those first stars began to reveal itself, a consequence far more tangible than light. That ferocious light, it was just the start. Those first stars, those titans of pure hydrogen, they were living on borrowed time. With that much mass, that runaway furnace, they burned through their fuel in just a few million years. A cosmic heartbeat. And when the fuel ran out, the balance shattered. Gravity had been held back by the outward push of fusion, and then suddenly it had no opponent. It won in an instant. The star's core, with nothing holding it up, collapsed inward at a huge fraction of light speed, and then it rebounded. What happened next wasn't a quiet fade. It was a supernova, but not like the ones we see now. These were pair instability supernova, so violent, so complete, they left nothing behind. No black hole, no neutron star. Just pure energy. In that final flash, a single star could outshine an entire modern galaxy. The universe's first true cataclysm, but inside that destruction, something was being born. For millions of years, the nuclear fires in those cores had been doing more than making light. They'd been running a cosmic forge. Starting with hydrogen, fusion built helium. Then, under all that weight and heat, helium fused into carbon, carbon into oxygen, the chain went on. Neon, magnesium, silicon. Finally, in the star's last days, iron. For the first time, the universe wasn't just hydrogen and helium. New atoms existed. Carbon, oxygen, nitrogen. The very elements that are the bedrock of planets, of oceans, of life. But they were trapped, locked in the dying heart of the star, until the supernova. The shockwave from that explosion did more than tear the star apart. It became a crucible. In the insane heat and pressure, elements heavier than iron were forged. Gold, silver, uranium. Every atom of that stuff in your jewelry, in your phone, in the world around you, was born in a cataclysm like that. And then the explosion did the most important thing. It took all this new, complex material and hurled it out into space. A cosmic scattering of seeds. The pristine gas clouds, once only hydrogen and helium, were now polluted. Enriched. They contained the ashes of dead stars, the universe's first act of recycling. And that changed everything. The next generation of stars that formed from those clouds were different. They had traces of carbon, oxygen, iron. Those new elements acted like a coolant, letting the gas collapse into smaller, more stable structures. These were the first population II stars. And from the material swirling around them, the first solid things could form: rocks, ice, dust, the ingredients for planets. So the death of those first monsters wasn't an end. It was a necessary sacrifice. Their violent ends seeded the cosmos with the complexity for everything that came after. Our sun, our Earth, every atom in our bodies beyond hydrogen, it's stardust. We are the legacy of those first impossible explosions. The universe learned how to die. And in doing that, it learned how to build. The echoes from those first explosions are still reaching us. They've been traveling for 13.8 billion years. But they don't arrive the way you'd think. The light from that dawn has been stretched, pulled thin by the expansion of the universe. That brilliant blue-white flash has shifted down through the spectrum into the infrared. It's a faint, deep red glow now, a whisper of heat, invisible to our eyes. So to know this story is true, we build time machines. Our most powerful telescopes aren't just windows into space. They're portals into the deep past. They collect light that's traveled for billions of years so we can look back. We see galaxies not as they are, but as they were when that light began its journey. To see the very first stars, we look for the faintest, reddest smudges. The light from population III stars is so ancient, so stretched, it only exists in the infrared. That's why the James Webb Space Telescope is a revolution. It's an infrared observatory, chilled to near absolute zero so its own heat doesn't blind it. It's built to catch that specific, stretched whisper from the edge of time. The search is a cosmic detective story. Astronomers aren't looking for a single, pinpoint first star. They're hunting for clues in the collective light of the first infant galaxies. They look for a specific chemical fingerprint, the signature of a universe without heavy elements. They search for the telltale bubbles of reionization patches where the hydrogen fog was burned away earliest. Each faint, red galaxy they find pushes our view a little further back, a little closer to that moment of ignition. It's painstaking work, interpreting a signal that's been traveling for over 95% of the universe's history. Every photon is a piece of evidence. This is the frontier. We're using engineering marvels in the silent cold of space to answer fundamental questions. Where did we come from? How did the lights turn on? The story of the first stars isn't just a theoretical idea anymore. It's a hypothesis we're now testing, pixel by pixel, in the deepest images of the cosmos ever taken. We're witnessing the universe's childhood in delayed transmission. And what we find there doesn't just tell us about the past. It tells us about the nature of reality, and our place within a story that began with a single point of light in an endless dark. Those stars were brilliant, but they weren't the only ones building the dawn. They were actors on a stage, and the stage was built by something else, something we can't see. Dark matter, the invisible director of the whole cosmic show. The first stars gave us the light, but dark matter gave us the infrastructure. Think about those mini-halos where the first stars were born. What held them together? The hydrogen gas alone wasn't enough. It was too hot, too energetic. It would have just spread out. The gravitational glue came from something else. A mysterious, invisible substance. It makes up most of the matter in the universe. It doesn't shine. It doesn't absorb light. It doesn't interact with electromagnetic force at all. It passes through normal matter like a ghost. But it has mass, and with mass comes gravity. In the early universe, dark matter was already clumping together, drawn by its own gravity. Long before the ordinary gas could cool and collapse, it formed these vast, diffuse clouds. Halos, they acted as gravitational anchors. Deep potential wells, cosmic pits, and the normal hydrogen and helium gas flowed into them. The dark matter created the template, the invisible scaffold. Without that gravitational foundation, the primordial gas would have stayed a thin, featureless fog. it would have taken far, far longer for stars to form. If they ever did. Dark matter's pull gathered the fuel, concentrated it. It orchestrated where all the visible matter went. So when we picture that first star igniting, we have to picture it happening at the heart of a massive, invisible sphere of dark matter. A sphere the star could never see or touch, but its influence was absolute. This is the dance between the seen and the unseen universe. The luminous stars we study are just the bright tracers, the visible markers of a much larger, hidden architecture. Every galaxy we see today, our own Milky Way, is embedded in a much vaster halo of this dark matter. It's the framework the cosmos is built on. So the story of the first light is also a story about a partnership between the ordinary matter that learned to shine and the dark matter that taught it where to gather. One provided the fire, the other provided the hearth. The invisible architecture of dark matter set the stage. The birth of the first stars was a theory. A logical story, but one we couldn't see. So we build the universe from scratch. We recreate that dawn inside a machine. That's supercomputer cosmology. Scientists don't just imagine the first stars. They grow them in a simulation. They start with a digital universe, a vast box of simulated space. They fill it with the precise ingredients from just after the Big Bang. The right amounts of dark matter, hydrogen, helium. They set the initial conditions from our best measurements of the cosmic microwave background. And then they press play. They let the laws of physics run their course. Gravity, fluid dynamics, radiation, chemistry. The simulation calculates the interactions between trillions of virtual particles. Over hundreds of millions of virtual years. It's not a pre-rendered animation. It's a numerical experiment. A staggeringly complex one. Every gravitational tug, every collision of gas clouds, every photon of radiation is accounted for by equations. And we watch. We watch the dark matter begin to clump, forming that invisible web. We watch the gas flow into the gravitational wells, cooling and condensing. We wait to see if a point of nuclear ignition flares to life in the data. These simulations are our time machines. They show us the first stars didn't appear in grand, glittering galaxies. They were pioneers, often born alone or in tiny, fragile clusters at the nodes of the dark matter web. Isolated beacons in a vast, dark ocean. The simulations reveal their likely masses, confirming they were probably giants. They show how their fierce, ultraviolet radiation begins to carve those first, tentative bubbles in the fog. This virtual universe is a testing ground. If our theories are wrong, the simulation won't produce stars that match the faint, ancient light we're starting to see. It's a constant dialogue between prediction and observation. And these simulations act as a treasure map. They tell observers where to look. By predicting the properties of the very first galaxies, how bright they should be, what color their light should be stretched to. They give missions like the James Webb Space Telescope a hunting strategy. They point to specific patches of sky, specific signatures to search for. So when Webb detects a faint red smudge from the edge of time, it's not just a lucky find. It's often the confirmation of a universe that was born first in lines of code. We are testing the story of our origins by attempting to write the first chapter ourselves. And seeing if the universe agrees. To understand that darkness, you listen for its echo. A faint, cold whisper that fills all of space. The cosmic microwave background. It's the oldest light we can see. A snapshot from when the universe was 380,000 years old. A cosmic baby picture, before the first stars. Before the Dark Ages even started. This glow is remnant heat from the Big Bang itself, released when the universe cooled enough for atoms to form, when light could travel freely for the first time. We see it now as microwaves, a uniform, cold bath of radiation just a few degrees above absolute zero, the afterglow of creation, and it holds the blueprint for everything that came later. If you could see it, the whole sky would glow with a soft, pearlescent light. But cosmologists don't see a smooth picture. They measure its temperature with incredible precision. And they find it's not perfectly uniform. There are tiny variations, ripples in the temperature, warmer spots and cooler spots, differences of just 1 part in 100,000. These are the cosmic seeds, the same density wrinkles, those quantum fluctuations from the universe's first instant, now frozen into light. They mark where matter was slightly denser. The gravitational anchors that would, hundreds of millions of years later, pull in gas to form the first mini-halos and the first stars, so the cosmic microwave background is a map. A map of potential. It shows where the story was destined to begin, but it's more than a baby picture. It's also a canvas, because the story of the first stars left a mark on it. As those early beacons began to burn, their fierce ultraviolet radiation started to reionize the hydrogen fog. That process of stripping electrons didn't just clear the fog. It subtly affected the ancient light traveling through it. It imprinted a specific pattern on the polarization of the cosmic microwave background, a faint swirl in the light's orientation. An incredibly subtle signal, but it's there. It's the signature of the first starlight beginning its work, etched onto the oldest light we know. So this ancient echo serves 2 purposes. It shows the pristine conditions before the first dawn, and it carries the faintest fingerprint of that dawn's beginning. We're reading the universe's autobiography. Written in the language of temperature and light, the universe is 13.8 billion years old. That number is hard to hold, so you can think of it as a calendar year. The Big Bang is midnight on January 1st. In that year, the first stars don't show up until late January. That's how long the Dark Ages were. For about 180 million years after the beginning, there was no new light. Just the afterglow, cooling and fading. It was quiet. The seeds were there, but they were whispers. Then, between late January and early February, something changed. In the densest parts of the web, the first protostars crossed a line. Fusion ignited. A pinprick of blue-white light. Then another and another. That was the cosmic dawn. The first sparks. This period, from 180 million to 500 million years after the Big Bang, is the epoch of reionization, the universe's adolescence. Those first stars and the early galaxies began burning bubbles in the hydrogen fog. It wasn't even. Some regions cleared early. Others stayed dark longer. It was like a continent after an ice age. The ice doesn't melt all at once. First lakes, then channels. Isolated peaks become islands. Over hundreds of millions of years, the landscape is revealed. That was reionization. The fog was being destroyed by starlight. By the time the universe was 1 billion years old, the transition was mostly done. The fog was gone. The universe became transparent. On the cosmic calendar, that's around mid-March. So from the first spark to a clear cosmos, the whole thing took less than 10% of the universe's current age. It was a fast, violent puberty, and it set the stage for everything after. For nearly 90% of cosmic history since then, light can travel freely. Stories written in starlight can be told across the gulfs between galaxies. Our entire view of the deep cosmos depends on that ancient clearing. Light has a signature we can see. But the dark had a sound, a low hum that was everywhere before the first stars. That hum came from the most common thing in the universe back then: neutral hydrogen. The atom itself sings. It sings at one specific pitch, a radio wavelength of 21 centimeters. That's the hydrogen line. You couldn't hear it, but to a radio telescope, it's a clear tone. For all those millions of years of darkness, this 21-centimeter hum was just there. A background noise of pure hydrogen, a radio echo of the void. Then the first stars turned on. Their ultraviolet light started to destroy the thing making the sound. Where a star shone, it ionized the hydrogen. It stripped the electrons away. And a hydrogen atom that's ionized can't sing that 21-centimeter song anymore. So as the bubbles of reionization grew, they weren't just clearing a visual fog. They were making bubbles of radio silence. Think of a huge forest filled with the sound of one kind of cricket. Then, in patches, the crickets go quiet. Not because they leave, but because something changes them. The silence becomes the signal. The pattern of the quiet shows you where the change is happening. That's what astronomers are trying to hear. They're building the most sensitive radio ears on Earth and in space to listen for that ancient pattern of sound and silence. Projects like the upcoming Square Kilometre Array are made for this one job: to tune into the universe's oldest radio station. The signal thereafter is incredibly faint. It's been traveling for over 13 billion years, stretched and thinned out by the expansion of the universe. Finding it is like trying to hear a whisper from across an ocean in a storm. But if they can map it, it would change everything. It would give us a three-dimensional acoustic map of the cosmic dawn. We could hear, in radio waves, the dark ages ending. We could listen as the first bubbles of silence appear and grow and finally merge. This map would show us the process in a way light can't. Light shows us the bright sources, the stars themselves. But this radio map would show us the shadow they cast on the hydrogen fog. It would show the negative space, the shape of the emptiness they made. It's a completely different sense for understanding the same event. We'd go from watching the bonfires to mapping the retreating mist around them. That's the promise. To not just see the dawn, but to hear the night recede. That radio silence, that quiet, it points to something bigger. The first stars weren't just lights. They were knots, the first knots in a net. Their energy and the elements from their deaths started weaving the fabric we see now. That fabric is the cosmic web. And those early stars were its architects. When one of those first stars exploded, it did two things. It scattered heavy elements, yes, but it also sent a shockwave. A blast of energy and hot gas that pushed everything around it. It carved out cavities in the primordial hydrogen, like a bubble rising in thick soup. The material gets pushed aside and it piles up at the edges. That's what these supernova bubbles did. They swept up gas, compressing it into dense shells. And in those shells, conditions were right for what came next. The enriched gas, now with carbon and oxygen, could cool better. It could fragment into smaller, denser clumps. This is where the second generation of stars formed. Not alone, but in clusters, along the rims of these enormous, expanding bubbles. The universe was learning to build in groups. It wasn't about single, monstrous stars anymore. It was about communities. And these stellar communities, held by gravity, linked by a shared origin in an earlier explosion, they became the seeds of the first true galaxies. The explosions didn't just spread ingredients. They sculpted the nursery. They created the dense environments where gravity could do its next phase of work. On a much larger scale, this feedback loop was crucial. A star forms, lives, explodes. That explosion enriches and compresses nearby gas, triggering more stars. Those new stars then live and die, continuing the cycle. But there's another side to this, a regulating force. Those first stars didn't just explode at the end. For their whole, brief lives, they flooded their surroundings with intense radiation. This radiation heated the nearby gas clouds. It kept them warm. And warm gas is hard to collapse. It's like trying to make a snowball with slush. The heat provides pressure that fights gravity's pull. This heating put a brake on star formation. It prevented every cloud from immediately turning into stars. It forced the universe to be selective, to form stars only in the densest, most sheltered pockets where gravity could win. This regulation is why galaxies aren't just solid balls of stars, why they have structure, why star formation happens in bursts, not in a single rush. That early radiation, that cosmic pressure, helped determine the sizes of galaxies. In regions where the feedback was extremely strong, it could blow gas away entirely, stunting a galaxy's growth, leading to smaller, dwarf galaxies. In regions where it was more balanced, gas could cool in cycles, allowing for larger, spiral galaxies like our Milky Way to form over time. So the legacy of the first stars is written in the variety of the cosmos. The majestic spirals, the giant ellipticals, the faint dwarfs. This galactic diversity has its roots in the chaotic, energetic beginnings of those first furnaces. They didn't just end the darkness, they began a conversation. A push and pull between creation and destruction, between heating and cooling, that has shaped every galaxy we see. Their light was the first word in a story of structure that built the universe from a simple fog into the grand, intricate web we call home. The first light might not have come from a star. There's another possibility, a more violent one, a cosmic shortcut. The first luminous object could have been a feeding black hole. That's the black hole dawn scenario. It starts with an anomaly, a vast cloud of primordial gas that doesn't fragment into stars. Something prevents it from cooling. Maybe it's in a dense knot of dark matter, or bathed in strong radiation, so the cloud collapses as one single entity. It skips the star stage, it falls directly into itself, and at its center, a black hole is born. A seed of immense gravity from the start. This isn't a black hole from a dead star. This is a direct collapse black hole, thousands of times the mass of the Sun appearing in the dark. And then it begins to feed. A whirlpool of gas forms around it, a superheated disk spiraling inward. The gas doesn't fuse, it just gets hot, unimaginably hot. Millions of degrees, it glows with fierce light, pouring out ultraviolet and X-rays, an accreting black hole. A quasar in its earliest form, the light would be different. A star's light is a controlled burn, steady. A feeding black hole's light is chaos, the scream of matter being destroyed. It would flicker, variable. And its radiation would be harsher, more penetrating. It would ionize the surrounding hydrogen fog not with a gentle bleach, but with a blistering assault. If these black hole beacons were common, reionization would have looked different. The bubbles they carved might have been sharper, more defined. The pattern of the clearing would carry a signature of violence, not the widespread glow of stars. So how do we tell which dawn happened? Astronomers look at the deepest data. They scrutinize the most distant quasars. Are they too old, too powerful to come from a dead star? Could they be the direct collapse monsters themselves? Others look at the statistical pattern of reionization. Does the patchwork match a universe lit by stars, or one punctuated by these pinpoint black hole engines? This investigation is a reminder. Our story of the first light is still being written. It's a hypothesis. The universe's first chapters are not settled history. They're a frontier. The black hole dawn challenges our assumptions. It suggests the cosmos might have taken a shortcut, leaping straight to the most extreme objects. It keeps the mystery alive. For now, the first stars are the best explanation. But the universe has surprised us before. And in that slim chance of a different dawn, we find the spirit of exploration. Not just confirming what we expect, but remaining open to the plot twists written in the faint light from the edge of time. The fine-tuning of that first dawn wasn't an accident. It was a prerequisite. Those first stars, their immense mass, their furious lives, their cataclysmic deaths, they set a chemical clock ticking. They produced the first heavy elements in a very particular ratio: carbon, oxygen, nitrogen, iron. That initial blend was the starter culture. It dictated the chemistry of the second generation of stars. And those stars forged more. Each cycle built on the last, enriching the cosmos with the periodic table we know. But if the recipe had been different? Imagine if those first stars were smaller, more modest. They might have burned for billions of years like red dwarfs, fading to white dwarfs without a supernova. A quiet end. And in that quiet, the universe would have remained chemically sterile. Just hydrogen, helium, a trace of lithium. No carbon for organic molecules. No oxygen for water. No iron for planetary cores. The cosmic kitchen would have had only the most basic ingredients. Forever, no rocks, no oceans, no planets. And certainly no life. So the violent, wasteful death of those giants wasn't a tragedy. It was a necessity. It was the universe learning to cook. The timing was just as critical. Reionization had to happen, but it had to happen in a certain way. If it was too abrupt, too intense, If those first black holes or stars scorched the cosmos clean too quickly, they could have blown apart the delicate gas clouds. The clouds needed to form the next galaxies. It could have sterilized vast regions of space, but if it was too slow, the fog might have lingered, stifling the growth of structure. The Milky Way, with its specific spiral shape, its sheltered neighborhood, might never have assembled. Our cosmic address is a product of that ancient, balanced clearing. A universe forever in a dark age, or one violently ionized in an instant. That would be a universe of isolated monsters or perpetual simplicity. Neither is a promising nursery for complexity. This leads to a reflection. The conditions that ended the Dark Ages appear to be precisely the conditions required for observers like us to eventually exist. The masses of the first stars, the rate of reionization, the yield of those first supernovae, they all fall within a narrow range, a range that allows for planets, chemistry, biology. This is often called the Anthropic Principle, the idea that the universe we observe must be compatible with the existence of observers. It's not that the universe was made for us, but in a vast ensemble of possible universes, with different physical laws and different initial conditions, we find ourselves in one of the rare versions where the story could be told, where stars could forge the elements of life, and where those elements could eventually coalesce into beings who look back and wonder how it all began. Our existence is a data point, a clue. It tells us the first dawn wasn't just any dawn. It was the specific kind of dawn that leads, 13.8 billion years later, to a world with forests and oceans and mines. Mines capable of tracing their own origin to a flash of light in the void. We are not separate from that ancient history. We are its most recent expression. The story of the first stars is, in the deepest sense, the opening chapter of our own autobiography. That autobiography is written in the faintest ink. You have to become a cosmic detective to read it, looking for clues that time and distance have almost erased. And detecting the light from the first stars is probably the hardest thing we try to do in astronomy. You have to think about what we're looking for. Galaxies from when the universe was just a few 100 million years old. They aren't the big spirals we know. They're these tiny, fragile infant things, and they're moving away from us at a huge fraction of light speed. That motion stretches their light, pulling it out of the visible range and deep into the infrared. So the brilliant blue-white starlight that left those galaxies arrives here as just a dim, deep red glow. A whisper of heat, but then there's our atmosphere. It's a glowing barrier. It shines brightly in the exact infrared wavelengths we need. It's like trying to see faint stars at twilight when the sky itself is still bright. From the ground, the signal is completely washed out, so you have to go above it. You have to put observatories in the silent cold of space. That's why something like the James Webb Space Telescope isn't just an upgrade. It's a necessity. It's our only set of eyes for that era. Webb's instruments are chilled to just a few degrees above absolute zero, so its own heat doesn't blind it to that ancient warmth it's searching for. But even with a perfect telescope in space, the challenge is still immense. The sky isn't empty. It's filled with foreground objects, billions of closer, brighter galaxies from later times. They crowd the view, and the trick is to find the few faint red smudges that aren't just distant, but primordially distant. Astronomers don't just take a picture. They take a spectrum. They spread the light from each candidate galaxy out into a rainbow, looking for a specific drop in intensity. That drop is caused by neutral hydrogen in the way, absorbing certain wavelengths. It's like a cosmic timestamp. It confirms you're looking back into the era of fog, before reionization finished, and the data itself is a minefield of noise. Instrumental artifacts, cosmic rays hitting the detector, the faint glow of zodiacal dust in our own solar system, all of it creates a contaminating haze. Pulling the true cosmic signal out of that foreground contamination is a monumental task of data processing. It needs complex statistical filters and algorithms, applied painstakingly by teams of scientists. They aren't just looking through a telescope. They're digitally excavating, brushing away the dust of eons to see the shape of the first dawn. It's a hunt for needles in a cosmic haystack, where the haystack is the entire visible universe, and the needles are photons that have been traveling for over 13 billion years. Every confirmed detection is a triumph, a whisper successfully pulled from the roar of time. Looking for that first light, it's not just data, it's something older. Long before telescopes, people told stories about a world coming out of darkness. A void, a deep, a great night. And from that, a first light appears. In so many creation myths, light is the first act, the word that separates day from night. It's the basic metaphor, order from chaos, knowledge from ignorance. And now our science, finding the cosmic dawn, it echoes that same arc. We've found it, written in physics, in the faint glow of infrared galaxies, our universe's version of that story. The Dark Ages were the cosmic void. The first stars igniting, that was the command, let there be light. That parallel isn't just chance. It points to a human intuition about how beginnings work. That from simplicity comes complexity, from uniformity, diversity, and from darkness, light. Science has given that intuition a timeline, a mechanism. Characters made of gas and gravity. But the feeling, the sense of a sacred transition, that stays. The cosmic dawn is when the universe became more than expanding space and cooling particles. It became a place where things could happen, where structure could grow, where complexity started pointing upward. Before that, the cosmos was uniform. Simple, quiet. After it was a canvas, it had gradients, temperatures, differences, places hot and bright, places cold and dark. That shift from simple to complex might be the most important event after the Big Bang itself. Because complexity is what you need for everything we care about. For chemistry, planets, oceans, life. For minds that can look up and wonder. Thinking about this gives you a humbling view. We're not just living in the universe. We're a result of its long journey from that initial simplicity. Every atom in us beyond hydrogen came from stars that lived and died because that first dawn happened. We are made from starlight, processed through generations of cosmic evolution. That bridges a gap between the cold equations of cosmology and the warm experience of being human. Between discovery and wonder. Knowing the science doesn't shrink the awe, it deepens it. It grounds our oldest stories in a new, evidence-based epoch. We're part of a continuity that goes back to the first flicker in the dark. Our search to understand the cosmic dawn. In a real way, that's the universe starting to understand itself. Through us, it looks back at its own childhood. It pieces together how it grew up. That connection turns astronomy from a distant science into something personal. We're not just studying the past. We're uncovering our own cosmic ancestry written in the light that ended the long night. The whispers Webb picks up, they are just pieces. The first pieces of that old story. To really understand the dawn, we need more ears, sharper eyes, and the next time machines are already being planned. Each one listens for a different part of the echo. Take the Nancy Grace Roman Space Telescope. It's launching later this decade. It won't just stare at one spot. It'll do a sweep, a huge survey. Think about trying to understand a whole forest by looking at one tree. That's a deep field image. Now imagine having a map of the entire forest. Where the trees are, where the clearings are, where the oldest groves stand. That's what Roman does. Its wide view will find the earliest galaxies. The rare ones Webb might miss because they're outside its narrow gaze. It'll give us the numbers, the statistics of the infant universe, a kind of census. But to see inside those first galaxies, you need even more power. So there are concepts. LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, or HAB-X, the Habitable Exoplanet Observatory. These are visions, telescopes on a staggering scale. Mirrors many times bigger than Webb's. Their resolution would be so fine they might do something that seems impossible. They could directly image the disks. The swirling gas and dust inside an early galaxy. You could watch, in one snapshot across billions of years, the nurseries, where the second and third generations of stars were being born. You could see the architecture, the first cities of stars, and on the ground a colossal eye is being built, the extremely large telescope, the ULT, in the high deserts of Chile. Its main mirror will be nearly half a football field long, a mosaic of almost 800 segments. It will gather more light than any ground telescope ever. Our atmosphere blurs things, it glows, but advanced systems will counteract that distortion. Thousands of times a second, the images could be sharper than Hubble's. The ELT will take spectra of these earliest galaxies with incredible detail, reading the chemical fingerprints, telling us exactly what they were made of, how fast they were forging new elements. So each of these observatories in space on Earth, they are tools for cosmic archaeology. Webb is the delicate brush. It uncovers the first artifacts. Roman will be the surveyor's map. It shows us where to dig. The ELT is the high-powered microscope. It analyzes the composition. And future giants like Louvoir would be like satellite imagery, revealing the full layout of the ancient landscape. Together, it's a campaign, a multi-decade effort to collect the fading whispers. The first starlight, before it's lost to time and expansion, they're not just tools. They're extensions of our curiosity, built to answer the most fundamental question. Where did all of this come from? And with every new lens we point at the darkness, that first dawn, that moment of ignition, it comes into a little sharper focus. Their internal design was this perfect, simple engine. To imagine a population 3-star, you have to set aside everything you know about stars like our Sun. Our Sun has layers like an onion. There's a radiative zone where energy bounces, and a convective zone where hot plasma rises. It's a complex structure because it contains heavier elements: carbon, oxygen, iron. These act like impurities. They absorb light, and that changes how heat moves. But the first stars were pure, just hydrogen and helium, and that purity created something completely different. At its heart, the core was this seething, churning cauldron. Because there were no metals to create opacity, to block energy, the heat from fusion could move outward with brutal efficiency. So the star didn't need separate zones. Instead, it likely had a convective core that was massive, spanning most of its entire radius. Picture a pot of water boiling violently. The whole interior was one giant, rolling boil. This constant, turbulent mixing acted as a supercharger. It brought fresh hydrogen fuel into the furnace at the center and swept the helium ash away. It meant the star burned its fuel completely and with terrifying speed. There was no wasted potential. It was a perfect, self-stoking fire, and that fire showed on the surface. What we'd call the star's skin, its photosphere, wasn't a place of gentle, yellow light. It was a maelstrom of energy. The temperature there was staggering, likely over 100,000 degrees. Our Sun's surface, for comparison, is about 10,000. This extreme heat meant the star didn't glow white or blue as we'd see it. It emitted most of its light in the far ultraviolet, a wavelength our eyes can't perceive. It was a color of pure violence. To any primordial hydrogen atom nearby, this wasn't just light. It was a barrage of tiny, high-energy bullets, each one perfectly tuned to rip electrons away. That's why they were so devastatingly effective at reionization. They weren't just bright. They were biologically invisible assassins, shredding the cosmic fog with a color we can't even see. This internal simplicity dictated their entire fate. That efficient, churning core meant they lived fast. A star hundreds of times the mass of our Sun could exhaust its fuel in just 2 or 3 million years. A cosmic mayfly, and when the fuel ran out, the collapse was total. Their deaths weren't the gentle sighs of smaller stars. They were pair instability supernova. Explosions so complete they vaporized the entire star, leaving no remnant behind. Ephemeral titans, perfect fusion machines born from simplicity, whose very perfection guaranteed their spectacular and total demise. We have no modern analog to study. Every star we can point a telescope at is polluted, complex, and tame compared to those first, pristine, and perfectly violent engines of light. The perfect, violent efficiency of those first stars was also their expiration date. A star that burns through everything in a few million years, it doesn't just die. It sets a timer for its own kind of existence. The universe could only make those pristine, monolithic giants for a short window. Because when the first one exploded, the recipe was altered forever. That supernova didn't just scatter light. It scattered the very thing that would end the era of the giants. Metals, to an astronomer, a metal is any element heavier than helium. Carbon, oxygen, silicon, iron, the ash from those first furnaces, and even a trace amount of this ash sprinkled into a gas cloud changes everything. It acts like a cosmic coolant. A single dust grain of carbon or silicon can radiate heat away far more efficiently than simple hydrogen ever could. That's the critical shift. Before, gas clouds had to struggle to cool. They could only collapse into the largest, most massive clumps. Now, with metals present, the clouds could chill faster. They could lose the thermal pressure that fought gravity. And as they collapsed, they didn't just form one giant core. They could fragment. They could splinter into many smaller, denser knots. Think of a cloud of steam. It's uniform. If it condenses, it might form one large droplet. But if you introduce dust particles, each speck becomes a nucleus. A place for water to condense. You get a mist of countless tiny droplets. That's what metals did. They provided the seeds for fragmentation. The result was a new generation. Astronomers call them population 2. They were different. They contained those traces of metals forged in their ancestors, and because they formed from fragmenting clouds, they were born with a range of sizes, but they tended to be much smaller. No longer hundreds of times the mass of the Sun. Many were like our Sun, or even smaller. A revolution in scale. The age of the isolated, monstrous beacons was over. In its place came communities. Population 2 stars rarely formed alone. They were born in clusters from those same fragmenting clouds, swarms of siblings bound by gravity. The beginning of true stellar societies. The kind that would later build the globular clusters orbiting galaxies like ancient fossils. And this change changed the universe's character. Smaller stars live longer. Billions of years instead of millions, they burn steadily, predictably. They provide stable environments. The chaotic, blistering violence of the first dawn gave way to a more sustained, orderly glow. A cosmic ecology emerged. Stars of different masses playing different roles. The long-lived smaller stars provided stability. The occasional remaining massive stars, now also metal-enriched, would still explode. But their deaths were different, often leaving behind neutron stars or black holes, continuing the cycle. The first stars, by their spectacular deaths, engineered their own obsolescence. They sacrificed their unique, pristine nature to create the conditions for a richer, more diverse, more stable cosmic landscape. They were the pioneers who cleared the land and mined the first ores, so that countless smaller, more enduring settlements could eventually flourish. Their legacy wasn't their own longevity. It was the lasting complexity they made possible. The legacy of those first giants isn't completely gone. We might have found their grandchildren. Scattered in the halo of our own galaxy, the Milky Way, are some of the oldest stars we know. They're like cosmic fossils. They carry a chemical memory of that first generation. There's one star, catalogued as SMSSJ03, 1300.36. It's incredibly ancient, and it holds a key clue. It has almost no heavy elements. Its iron content is over 1 million times lower than our Sun's, but it does have trace amounts of other things: carbon, magnesium. That specific, lopsided chemical fingerprint is the telltale sign. Astronomers think this star formed from a gas cloud that was enriched by just one single event. One solitary population, 3 supernovae. The explosion of one of the universe's first stars. That makes these ancient halo stars something extraordinary. They're not the first stars themselves. They're the second generation, the direct offspring. And by studying the precise recipe of elements in their atmospheres, how much carbon versus iron, how much oxygen versus calcium, scientists can do a kind of cosmic reverse engineering. It's like finding a unique alloy in an ancient artifact and deducing the exact temperature and process of the forge that made it. From the chemical fingerprint in this nearby star, we can infer the mass of the long-dead progenitor. Was it 200 solar masses? 300? We can estimate the energy of its explosion. Was it a full pair instability event that blasted everything apart, or a slightly weaker collapse? Each ratio is a clue. So while we strain to see the faint infrared glow of the first galaxies at the edge of time, we also have these tangible, local relics. Stars we can observe in great detail right in our galactic backyard. Their light is a direct messenger from that primordial era. They're living archives. Their atmospheres haven't undergone the complex mixing of later galactic generations. They preserve, in their elemental abundances, a snapshot of the universe's first chemical steps. By reading this ancient stellar DNA, we connect the theoretical story of the cosmic dawn to a physical, observable record. These faint, old stars are the closest link we have to the titans whose light ended the Dark Ages. They're the enduring chemical signature, that first foundational act of creation. That perfect, churning fire, its physics, it was missing something. Magnetism, that hidden force, it's everywhere now, in sunspots, in jets from galaxies, but was it there then, at the very start? Did those first stars feel it? It adds a layer, a profound complexity. We imagine those pristine clouds collapsing, just gravity. But what if, from the beginning, they were threaded with invisible lines? Magnetic force. These fields, they're like cosmic elastic. They resist being squeezed. In a collapsing cloud, a magnetic field offers support. It pushes back against gravity's pull. That could have slowed it all down, maybe prevented the biggest clumps from forming so fast, or fragmented them differently. A star's birth isn't a straight fall. Gas collapses, it spins faster. Like a skater pulling in their arms, that rotation flattens everything into a disk, the feeding structure around a newborn star. And magnetic fields, they interact fiercely with that. They can act as brakes, taking rotational energy from the infant star, moving it out into the cloud. They can channel material, like guiding rails for the incoming gas. So even a weak primordial field, it could have changed the blueprint, fundamentally. It might have changed the ultimate masses. Were they 500 solar masses or 200? That difference is everything for how they lived, how they died. It could have dictated their spin, how fast they rotated, which affects their internal mixing, their lifetime. The origin of these first fields, it's a deep mystery. Were they seeded by quantum processes, right after the Big Bang, stretched to cosmic scales by inflation, or were they generated later, by the turbulent motions of the primordial plasma itself? Like a cosmic dynamo starting up in the dark, we don't know. To find out, theorists are building new simulations. This isn't just gravity and gas anymore. They're incorporating magnetohydrodynamics, that tangled physics, the complex dance where magnetic fields and moving plasma intertwine. Running these simulations is monstrous. Computationally, but early results, they suggest magnetism may not have been a minor detail. It could have been a decisive player, adding a subtle torque. A stabilizing force, something that shaped the distribution of those first stellar masses. It's another variable in an already intricate puzzle, a reminder. The universe's first steps toward light, they were likely guided by more than just gravity and heat. They were sculpted by invisible forces, forces we are only beginning to sense. Forces whose faint imprint might still be woven into the fabric of everything we see. That magnetic thread leads somewhere deeper. The Dark Ages weren't just an empty stage. They were a pristine laboratory, a place of profound simplicity. No stars, no galaxies, no complex chemistry. Just dark matter, hydrogen, helium, cooling in an expanding space. That simplicity is a physicist's dream. It lets us test ideas about the most fundamental laws, in a way we can't do now in today's messy, evolved cosmos. Take dark matter. We know it exists because of its gravity, but what is it? Our best guess is it's cold, slow-moving, and that it barely interacts with anything, even itself. That model works beautifully to explain the large-scale structure we see. But what if it's wrong? What if dark matter is warm, moving faster in the early universe? Or what if it does interact, through some unknown force, that would change everything about the first act? Warm or interacting dark matter would smooth out the smallest clumps. It would prevent the tiniest minihalos from forming. The first structures would be rarer. They would appear later, and that delay would echo forward, changing the timeline of the first stars. Pushing back the cosmic dawn, we can look for that signature in the pattern of the oldest galaxies we find. In the subtle statistics of the cosmic microwave background, the Dark Ages hold the answer. They were the universe's first and cleanest dark matter experiment, running over 100 million years ago, and we're just now collecting the data. But dark matter isn't the only mystery we can probe. The timing of reionization itself is a cosmic clock. It tells us how much ultraviolet light was produced and how quickly. Our standard story uses those first massive stars as the source. But what if something else contributed? Something exotic, decaying or annihilating particles from the early universe, a population of early black holes we haven't accounted for. Even the faintest glow from these exotic sources would have helped heat and ionize the hydrogen fog. It would have made reionization happen a little faster, or a little more evenly. By measuring the precise patchwork of that clearing using the 21-centimeter signal, or the polarization of the cosmic microwave background, we can put limits on these possibilities. We can say, the universe reionized this way, so there couldn't have been too much extra energy from unknown sources. We're ruling out whole categories of new physics. By studying an era before the first starlight, so this isn't just astronomy, it's fundamental physics disguised as a history lesson. The Dark Ages offer a unique environment, simpler than any lab we could ever build, where the only actors are the most basic particles and forces. By observing the outcome, the pattern of the first lights turning on, we are effectively looking back at the universe's first controlled experiment. An experiment testing gravity, particle physics, and the very nature of dark matter. Every new observation from the edge of time isn't just filling in a chapter. It's providing a data point for theories that seek to explain reality at its most fundamental level. The long night wasn't empty. It was a silent, running test. And we are finally learning how to read the results. We have all this new data now from our new time machines, and the question is, how do you go through it? It might not be one big computer that does it. It might be millions of people, millions of curious people. This search for the first dawn, it's turning into something everyone can do. There's a model for this, projects like Galaxy Zoo. They took these huge libraries of images from Hubble, from Sloan, and they just asked the public to look, to classify, to help. So a volunteer at home, they see an image of a distant galaxy. They get simple questions. Is it smooth or does it have features? Is it a spiral? That kind of pattern recognition, algorithms still can't do it like we can. And it works. So many discoveries, unusual galaxy mergers, new types of objects. These weren't found by an astronomer at a telescope. They were found by a teacher, a student, someone retired just browsing in the evening who saw something odd. Now, with the James Webb Telescope and what comes after, the data flood is even bigger. It's a torrent. And these earliest galaxies we're looking for, they're faint. They're strange. They don't look like galaxies today. An algorithm, it can be trained to find what we expect to see. But a human eye, just looking, guided by curiosity, it might spot the thing we didn't expect. The outlier, just a smudge of light that doesn't fit. That could be the clue. So these citizen science projects, they're adapting, getting ready. So anyone with an internet connection can help scan these deepest fields. Look for the pioneers, and this does something. It takes the origin story and it opens it up. For most of history, thinking about the beginning was for philosophers or priests. Then for centuries it was for scientists with the right tools. But now, this quest to understand the first light, you can actually touch it. You can log on. You can classify real data that no one has ever seen. You're part of the process. It creates this shared sense of discovery, this wonder. It goes beyond the academic. It turns the big question, where did we come from, into a project we all work on. So every person who stops to sort a galaxy or to look at a strange data point, they're taking part in this old, grand pursuit. They're helping to read that first chapter, the cosmic autobiography, written in the faintest light from the very start. That first dawn was a cosmic beginning. It went from a neutral darkness to a cosmos full of galaxies. The journey started by those first stars. It's the foundational story of everything. We've traced it, from quantum seeds to gravitational collapse. From a molecular chill to a nuclear fire. We followed how an opaque fog became a transparent sky. That moment of first ignition, it did more than end the cosmic dark ages. It set in motion every process that would lead to planets, to chemistry, and ultimately to life. It was the universe's first great act of becoming. And as we keep looking back with more powerful tools, we get closer to seeing that first sunrise. Not as a theory, but as a story written in the light we gather. Every atom in your body that isn't hydrogen was forged in a star. The oxygen you breathe. The carbon in your cells, the iron in your blood, all of it is stardust, processed through generations of cosmic evolution. That makes you, and everyone you know, a direct descendant of that ancient dawn. You are made from the legacy of the first light.